One of the things that we do to look at the energetics of the rotation about the carbon-carbon bond is we do what we call a conformational analysis. Of course, in ethane, there's only 2 carbons and therefore only one possible bond to explore. Before we complete this diagram, I'd like to turn your attention to an animation that represents this. So here's a conformational analysis for ethane. We have several different representations of ethane in the bottom row. So we have the ball and stick, we have the Newman projection, and then something called a seahorse, which is in a sense kind of a front view of a wedge and dash. Now fortunately for us, 2 hydrogens have been marked in blue, so we can follow the pattern here. The graph represents the energetics of the conformational analysis. The y-axis has energy. In this case, it shows kilocalories per mole. In my diagrams, I usually use kilojoules per mole. Right now, we're in the situation of a staggered conformation. You can see the blue hydrogens are 180 degrees relative to one another. If we allow rotation to occur, and the idea is that we're keeping the back carbon stationary and we're allowing the front carbon to rotate, and I'll stop it right there, you can see that now the hydrogens are eclipsed to one another. That conformation represents a high energy point, and so we'd say that this is the eclipsed conformation. If we allow the rotation to continue, we have another staggered conformation. If we allow the rotation to continue, we arrive at another eclipsed conformation. And again, more rotation takes us to another staggered conformation. And then finally, another eclipsed conformation. And then we would return, in a sense, to the original staggered conformation. So this is why I say that there are an infinite number of possible conformations, but we usually only look at 6 of them where they represent energy max and energy minimum. Let us turn to the notes where we can represent this in our own diagram. Now I've provided the number 12.7 kilojoules per mole to remind myself that that's the maximum difference in energy between the staggered and the eclipsed conformations. Now my x-axis is a little different. I am starting with an eclipsed conformer, and you can see that it has a maximum amount of energy. If you're asked to generate one of these diagrams, you'll see that we don't actually label the y-axis with absolute numbers, but we're looking at relative energies. And so we're going to be, in a sense, moving to the right here. And in my particular case, we're going to keep the front carbon stationary. So here's the front carbon represented by this red dot. And you can see that in all of these cases, the front carbon has the exact same orientation. But what we'll do is we'll allow the back carbon to rotate. And it's rotating in a sense like this. So if we have a 60-degree rotation, we go from an eclipsed to a staggered. And we know the staggered will have a lower energy, so we'll draw a dot down here. If we allow another 60-degree rotation, well, then we'll arrive at another eclipse. Now, one of the things that we'll always need to consider is how do the energies of the 2 eclipsed conformers compare? In this case, there's no way of distinguishing between these conformers, so I'd say the energies would be essentially identical. Now, I'm not going to get a ruler out on your diagram to make sure it's perfectly aligned, but it should be pretty clear that the energies are relatively the same. If we allow further rotation, another 60 degrees, we arrive at another staggered. And sure enough, this conformer will have the same energy as the previous staggered. You can imagine we just keep on doing this. More rotation, another 60 degrees, we arrive at another eclipsed, where we have maximum torsional strain. And then more rotation, we arrive at another staggered. And essentially we say 0 torsional strain. And then finally another rotation to bring us back to the original eclipsed. Now usually we like to join these, and my graph is not as pretty as the one that we see in the animation, but essentially we can predict that the energy will go up and down, up and down. One of the things that's likely occurring as this rotation is happening is that the structure will spend more time in the low energy conformation versus the high energy conformation. So if you picture that there's this rotation about the sigma bond, it wouldn't be an even regular rotation, but it would be a very fast passing through the high energy state and a slowing down through the lower energy state. But of course, if this is happening at thousands of times per second, it would be pretty hard to pick it out. So thus far, we've introduced the idea of torsional strain. Again, torsional strain has nothing to do with the atoms that are attached to the carbons, but rather it's the repulsion between the pairs of electrons. There's another kind of strain that affects a conformational analysis, and this is the steric strain. To exemplify this, I will compare a conformational analysis of butane to ethane. But first of all, I define steric strain, and this is the strain experienced by a molecule when the atoms that are not directly bonded to one another are close enough that their electron clouds interpenetrate. So what I mean by this is, first of all, let's just orient ourselves that indeed we have this torsional strain. And let me provide a little bit of a legend. So TS will of course represent torsional strain. And as you might imagine, I'm going to use the abbreviation SS, which will be steric strain. You, of course, can use these abbreviations as well. Now, indeed, the molecule here of butane will also have some torsional strain. And you may recognize that although we're showing this as a wedge and dash, these guys, these conformers, are in an eclipsed conformation. Now, in terms of the hydrogens here, the actual radius of the atom is relatively small. And so the electrons associated with one hydrogen and another hydrogen don't really interpenetrate. They don't come that close. But a methyl group is quite a bit larger. And so I'll kind of represent it like this, that the electron cloud, or the region where you're going to find some electron density, takes up a greater volume. And so in addition to having torsional strain, these methyl groups in this eclipsed conformation come close enough to one another that we also have this steric strain. These arrows that I'm using here are not meant to represent resonance forms. I'm just saying that you've got the steric strain as well as the torsional strain. Let's now try to apply this to a conformational analysis. Before we finish the graph that's in our notes, I'd like to turn to an animation. So here we have a representation of a conformation analysis for butane. Once again, we're starting in an eclipsed conformation. The eyeball is looking down carbons 2 to 3. So we could also do a conformational analysis of looking down carbons 1 and 2. But in this case, we're focusing on 2 down to 3. So you can see the eyeball is looking down the ball and stick. But of course, we could also think of the eyeball looking down the Newman projection, or the eyeball looking down the sawhorse. As rotation occurs, you can see that the back carbon is held stationary, and we go from an eclipsed conformer to a staggered. You can see the methyl groups are now off of one another by 60 degrees. If we allow further rotation, you can see that we arrive at another eclipsed. It maybe isn't a surprise to you, however, that this eclipsed is of a different energy than our first eclipse. And this is because the two CH3 groups are not sitting on top of one another, but rather we have a CH3 on top of a hydrogen and another CH3 on top of another hydrogen. This evidently is of a lower energy situation. If we allow further rotation, we arrive at another staggered. In this case, the methyl groups are a complete 180 degrees relative to one another. So in this case, not only does the molecule not have any torsional strain, it has minimal steric strain, as the methyl groups are as far away from one another as possible. Continuing the rotation, we arrive at another eclipse. And again, I think you can probably see that this eclipse is similar to the eclipse at 120 degrees. Therefore, they are of the same energy. We have a further rotation, and we have another staggered. And again, this staggered matches the stagger that occurred at 60 degrees. And then finally, a further rotation back to the original eclipsed conformation. Now you can see that there's some labeling in terms of names. The names that I'd like you to know about are those different staggered conformations. If the large groups are 180 degrees relative to one another, we call that an anti-conformation or an anti-staggered conformation. However, if the large groups are displaced by 60 degrees, then we refer to that as gauche. And that refers to both if the groups are to the right of one another or to the left. So some people may know from their French that gauche, of course, means left. But in this case, it's the same word regardless of whether it's to the right or to the left. Now let's turn to our notes so we can complete the diagram there. Anytime that you're going to do a conformational analysis, it's helpful to decide where you're going to put your eyeball and, in a sense, orient yourself with a wedge and dash structure. So if I put my eyeball right here and I look down carbons 1 to 2, I can see that this is going to represent an eclipsed conformation, and the methyl groups are going to be on top of one another. And so that's exactly what we see right here. So that's the highest energy situation. Once again, we're going to keep the front carbon stationary, and we will rotate the back carbon. Now I've put the Newman projections both on top of the graph and below the graph just so I can fit them in more easily. So if I show the rotation here, we'll end up going from our eclipse conformation to the staggered conformation. And you can see in this staggered conformation, the methyl groups are 60 degrees relative to one another. So we would call this the gauche, or the gauche staggered. This, of course, is of lower energy. And so I'm going to draw a dot right there. We allow for further rotation, and we end up arriving again at an eclipsed. But as we saw in the animation, this eclipsed is not quite as high energy. So I'm going to draw it right here. But note, any eclipsed is still higher energy than any of our staggered. I allow further rotation to occur, and we arrive at another staggered. And this is the staggered where the methyl groups are completely on the opposite side of one another. And so we call this the anti-staggered. And this, of course, will be of the lowest energy. Again, I don't have any numbers on my y-axis, so these are just relative energies. Again, a rotation by 60 degrees brings us to another eclipsed. Now the eclipse that occurs at 120 degrees and at 240 degrees will have the same energies. So I'll try to align them up to the same spot. We have further rotation. Another 60 degrees brings us to another staggered. The staggered that occurs at 60 degrees and at 300 degrees will have the same energy. So again, I try to line up the dots. And then finally, we have further rotation. And this brings us back to the original eclipsed. So of course, it would have the same energy. So now if we join the dots, we can see that it more or less looks like the diagram in our animation. And this is unlike the diagram that we drew for ethane in the sense that there are different energies for the eclipses and there are different energies for the staggered. I should mention, of course, that this staggered right here is called a gauche. For completeness, if we compare the maximum energy for our eclipsed, which would be up here, with the minimum energy for our best staggered, this difference in energy would be around 20 kilojoules per mole. Whereas, if I go back to my ethane conformational analysis and I compare the minimum energy for our staggered, and of course all the staggereds are the same, with the maximum energy for our eclipse, this difference is 12.7 kilojoules per mole. So as you might imagine, the difference between 12.7 and 20 represents the additional steric strain that occurs for our butane structure. In the next videos, we'll look at how we can apply some of these ideas to ring structures.